Hi there, students. Let me walk you through my analysis of the lab that we did in class today, the lab where a student tosses a ball upwards, the ball rises, the ball falls to the ground. Okay, so pretty simple free fall motion. And we have some questions that we can answer. Let's see here. So what is the initial velocity? What's the acceleration? What's the displacement? And things like that. Okay. So these are all on Canvas, and hopefully you're going to look at those to study for the test. Well, let's take a look at how do we find the initial velocity. So how does one find the initial velocity using both graphs, using both the vertical position y and the vertical velocity information? So let's take a look at both of those. If we look at this equation here, x is equal to 1/2 at squared plus vit, this is going to be your go-to equation when you analyze position versus time graphs. Okay, if the acceleration is 0, you will have a linear graph. Okay, you would have vit plus xi. That has the form of y equals mx plus b. It has a linear form, but that's only if a is 0. If a is 0, this whole term goes away. Okay, if the object is not moving at all, then you have no acceleration and you have no initial velocity, and you just would have x is equal to xi. That would just be a straight flat line. If you have no acceleration, then you would have a line that would be sloped up or a line that would be sloped down depending on the velocity. If it was positive, it would go up and to the right, and if the velocity is negative, it would go down and to the left. But if you do have a quadratic or a parabola, like we have here in this graph here, this position time graph, okay, then we must have an acceleration. All right, and that's exactly what we have. So let's take a look at this equation here, and let's compare it to the equation on Logger Pro. So this middle term, the term that is attached to the t, is going to be our initial velocity. And we can see that the initial velocity, this bt, that's my coefficient for t, and that b is 2.267 meters per second. Alrighty, and that's our initial velocity. If we look over here at the velocity time graph, I've clicked on the examine button on the velocity time, and that's what this box down here is telling us. And we can move it over, and the first data point says that at time 0 the velocity is 1.7. Okay, so it's not exactly the same as this over here, but we are comparing a position time graph which is more accurate than the velocity time graph, especially on the ends. But it's pretty close. It's not too far off. We could also come over here, and if we click on this graph here and we can click on the tangent button, it will give us the slope of the tangent lines along the curve. Okay, so if we zoom back way over here to the far left, the tangent of that first dot is 1.746. Okay, so much more in agreement with this guy over here. However, the curve fit tells us that it's a little bit higher than that. So that's okay. We could also look to see, for example, what is the slope at the very top of the curve. The slope, again, gives us the velocity. You can see the units of the slope are in meters per second, so that's velocity. So the tangent line at the top is really close to zero, negative 0.0420 meters per second, practically zero. And we can do the same over here. We can use the examine button to examine what it's like at the very, when does it reach about 0? It's in the same time, 0.233 seconds. It reaches that small speed, and over here, same time, same slope. Okay, and then we can see as the ball goes down, just before it hits, the slope gets really steep, and we can see that the slope is negative about 7 meters per second. Okay. And if we come over here and look at the examine button, if we examine the very last data point too, that's also about negative 7 meters per second. So we can see that what the initial velocity of the ball is, what the velocity of the ball at the top is, what the velocity of the ball just before hitting the ground is, and anywhere in between using either the tangent lines on the left graph or just simply reading the graph on the right. Again, this is velocity on the right and position on the left. Okay, so let's take a look at what the initial position is. If we look at this guy here, the initial position is the coefficient without a t attached to it. So it's just the plain constant. So here's our equation here, y equals at squared plus bt plus c. So c must be our initial position, 1.6 meters. In other words, as soon as we start collecting data, the ball is 1.62 meters above the ground. Another way of saying that is that that's when the student let go of the ball right here. Okay, and we can see that also on the graph. Now, how can we can't really tell from the velocity graph what the initial velocity is, but we can tell what the displacement is. In the first, 0.233 seconds, the ball goes from, from this height here. Let me click on the examine button here as well. Okay, so now I am examining. You can see that my y is 1.643 meters at the very beginning, and my y at the very top is 1.871. So I can subtract those two to get the displacement. All right. If I look at the velocity time graph, I can do the same thing. If I want to get the displacement on the way up, I can highlight this first part here where the ball is going up. Okay, leaving at a high positive velocity and then rising until it reaches a zero velocity. And if we calculate the area under that curve, if we fit the integral rather to it, we can see. I'm not going to take the time to blow it up, but you can see that velocity, or sorry, that change in position, the area is going to be 0.22 or so meters. Meters per second times second is meters. And so the displacement in that first little bit is 0.22 meters, which is exactly what we got when we subtracted this position from that position, about 0.22, a little over 0.2 meters. If we want to see what the displacement is in the second half, we know it rises. It has a maximum height of 1.871 meters, and it falls all the way to the ground at the very bottom, practically 0 meters at the bottom. If we wanted to, we could highlight the second half of this velocity time graph, okay? And that will give us, if we click on the integral function, that will give us the area of the second half, which is negative 1.772, call it negative 1.8 meters. And that's about what the ball did too. It fell about 1.8 meters from here to there. And of course, we can look at the entire displacement. The displacement, by the way, the area of the position time graph doesn't tell us anything. It's physically worthless. If we highlight everything over here, okay, we can calculate the area of this guy here, and that will give us the area of both the beginning and the end, which is negative 1.57, call it negative 1.6. And if we look over here, we go from 1.6 meters down to 0, and so that would also give us the displacement on this side. So the information is hidden in both of these graphs. Let's see, what else can we do? We've looked at the total displacement and the velocity of the ball before impact. I think that just about covers it. We could go into a lot more detail, but I think that's the big picture for this kind. How do we analyze this kind of graph? Hope this was helpful. Hope this helps you study for the test. Let me see. Is there anything I want to say before I go away? Let's see. I don't have much more to say except to say this. Look at what you're graphing. Always look first at what you're graphing. Here it's y versus time, the vertical position versus time, and here's velocity versus time, vertical velocity versus time. So students often think, oh, the slope tells us velocity or the slope tells us acceleration. That's not always true, right? The slope of what graph? The slope of the velocity time graph gives us the acceleration. Okay. Oh, we haven't talked about acceleration. Oh my goodness, we got to do that. So let's look at that here. So the slope of a velocity time graph gives us acceleration. The slope of a position time graph gives us velocity, Because this is a parabola, we can't find the slope of a parabola, but we can find the slope of the tangent lines. So that gives us velocity. The last thing to do is to figure out what is the acceleration. Sorry, I almost forgot about that. So let's take a look at the equation over here. If we look at the position graph, that equation is 1/2 at squared plus vit plus xi. So how do we find acceleration? Well, that a is part of the coefficient on the t squared term, and that a is acceleration. But notice that it's 1/2 of a is the coefficient. 1/2 of a is the coefficient. So if we click back over to the graph, then the a term, the capital A term here, that number is negative 4.8. And in the physics, that number represents, negative 4.8 represents 1/2 of the acceleration. So if we double this number, that will give us the acceleration. Or 4.8 is equal to 1/2 a. And so if we multiply both sides by 2, it tells us that a is around 9.6, which is pretty good. Okay. If we look, it's pretty good because acceleration should be negative 9.8. If we look at this graph, if we look at the velocity time graph, okay, how do we find the acceleration here? Well, the slope of the velocity time graph gives us the acceleration. And how do you remember that? Well, one thing is you could just look at the units, and that kind of gives you some clues. So slope is rise over run, and the rise of the velocity is meters per second, and the run in time is seconds, and so rise over run is meters per second, or meters per second squared, and that kind of gives us a hint that we're on to velocity. We're on to acceleration. So if we come over here to our equation sheet, here's another way you can figure it out. Now, what are we graphing? We're graphing velocity versus time, and this has the form of y equals mx plus b. Y equals some slope times x, some variable x, plus some y-intercept. And so that if you match this physics equation with y equals mx plus b, then the slope is a and the y-intercept is vi. Okay, so if we look over here, we see the slope of this line is negative 9.9. Okay, which is pretty close to negative 9.8, which is what we expect because I assume the kid's on Earth. The y-intercept here tells us the initial velocity, 2.261. Okay, and again, that comes from this equation. So when you're graphing velocity time graph, this is the equation you want. And when you're graphing position time graph, this is the equation you want to use to analyze. I guess the last thing I will say is, in intro physics, like physics first, we typically don't deal with accelerations that change. Okay, and so the velocity time graph gives us this slope like this, which is pretty constant, and that means that the acceleration is constant. If you have an acceleration that's non-zero, your y velocity is going to look like a diagonal line, either down and to the right, like this one is, a negative slope, or up and to the right, okay, which would be a positive slope. If you have a non-zero acceleration, then your position time graph will be a parabola. Here it's kind of a full parabola or over more than half of a parabola. So you have the ball going up, stopping, and coming down again. But you could have a parabola that goes down, stops, and goes up again. Okay, so that might be like a person on a bungee cord. You could also have parts of the parabola. You could have just the first part here where it goes from launch to the top. Or you could have it where it falls from the top at rest down to the bottom again. And of course, if you have the upside down parabola, you can have it from here to here, on the way down. And then you could have another shape might be from the ground up, or any portion of a parabola. All right, I think I've done way too much talking, but I'm hoping that students who are confused by this can see how everything is connected. The position time graph is connected to the velocity time graph, and some pretty unique ways.